Good afternoon, everyone. I'm a graduated student from Salle College. It's my honor to present the problem of paper cutting that's more formally known as the equidecomposition problem. Given two shapes A and B, if we can cut shape A into finitely many pieces, move and rotate the pieces to form shape B, then we say that shape A and B are equidecomposable. The word equidecomposable starts with the prefix EQUI. This suggests that it is something to do with equivalence, and actually is an equivalence relation. It can be proved that equidecomposition is transitive, and the reason is rather intuitive. We can dissect shape A into shape B, then shape B into shape C, overlap the two cuttings over each other, and we can get a dissection from shape A to shape C. It's a classical problem stating that every two polygons with the same area are equidecomposable. It is called the Wallace-Bolyai-Gerwin theorem. In this project, we are going to generalize the problem a bit to shapes with curves and also tighten the problem a bit such as restricting rotation. We have found out the exact conditions on whether two polygons are equidecomposable without rotation. We have also found the conditions on whether two figures with curves under certain restrictions are equidecomposable. In doing this project, we found some interesting facts. Every two polygons with equal area are equidecomposable even when only one rotation with 180 degrees is allowed. We also extend the problem to shapes with different area by allowing scaling, also known as dilation. We found out that every two polygons with the different area are equidecomposable when only one scaling and no rotation is allowed. Our proofs start at the most fundamental result, that's the lemma of parallelograms. Then the classical theorem follows. Then we extend the problem to weighted shapes. By these two results, we can prove whether two shapes are equidecomposable when rotation is not allowed. And together with the shape with curves, these four are the main theorems that is the backbone of the project. Then we are going to investigate some variants, for example, allowing scaling, and also in order to study the variants that involves limitation on rotation, the lemma of compression is needed. So the lemma of parallelogram states that every two parallelograms with the same area are equidecomposable. We can transform one parallelogram to another with equal base and height by shearing. So, yeah. And using a sequence of shearing, we can convert a parallelogram to any parallelogram with equal area. Weighted shapes are shapes with an integer weight on each point of it. Instead of treating shapes as opaque papers, we can treat them as semi-transparent plastic sheets that can overlap each other. We can even do addition and subtraction on shapes. It can be proved that equidecomposability in this case is equivalent to the original case. By considering weighted shapes instead of normal ones, we can avoid dealing with the case where two pieces overlap or exceed the boundary of the shape. Instead of proving shape A and shape B are equidecomposable, we can instead prove A minus B is equidecomposable to the shape consisting of nothing, and thus making the proof afterward easier to comprehend. We have seen that we can convert any polygons to another polygon with the same area. But what will happen if rotation is not allowed? We have seen that from a background image that a square can be dissected in 5 pieces, then combined into a square rotated 45 degrees. It's quite interesting that we can actually do rotation on squares or parallelograms without actually rotating any of the dissection pieces. This is the direct consequence of the lemma of parallelogram. The next question is, can we convert a square into a right angle isosceles triangle without using rotation? We can try doing so, but we will later find out that we are cutting more and more pieces. The answer is no. Notice the diagonal edge, the red line with the diagonal edge with the shape below it, and a green line with the shape above it. The two lengths is always equal. However, in the dissection of the rectangle isosceles triangle, the red line is always longer than the green line, so it's impossible. We have seen that the direction of the edge in the two shapes dictates the equidecomposability. We then define the direction distribution function that maps an angle to a real number. This is the total length of the edge with the direction specified by angle minus the total length of the edge with opposite direction. We will then show that two shapes are equidecomposable without rotation if and only if they have the same direction distribution function. To prove the theorem, we first subtract the two shapes to obtain a weighted shape, then convert the edge into horizontal or vertical ones. Then we cut the shape into rectangles, which can be easily handled by the lemma of parallelogram. Sometimes we want a shape to have a specific direction distribution function that can be fit in a small area. Therefore, we need the lemma of compression, which can compress a polygon to arbitrarily small size without affecting its direction distribution function. The proof of the lemma of compression involves cutting the shapes into pieces, then aligning the pieces together, and then stick all the pieces together to get a polygon. So with the lemma of compression, we can investigate on some interesting variant. For example, when only one rotation on one piece is allowed, while the other pieces can only undergo translation. The approach is to take out the polygon with specific direction distribution function that can be calculated. Then we rotate the piece, and then we apply the no rotation case on it. The lemma of compression is applied to obtain the polygon rotate. Another variant is that what happens when no rotation is allowed while a scaling on one piece is allowed. If the two polygons have different direction distribution function and the same area, scaling cannot be applied, so the direction distribution function remains unchanged. The two shapes are not equidecomposable under the restriction. If the two polygons have different areas, then we can take out the polygon that is scaled, then apply the no rotation case. The rest is similar to the one rotation case. The table shows that the number of scaling needed in different cases. Note that if two shapes have the same area but a different direction distribution function, then the number of scaling needed is 2. Because we can arbitrarily take out a polygon and then scale it, so to make the area different, then we can apply the one scaling no rotation case. So I'm going to talk about the shape with curves. But the above parts consider only shapes with straight edge, but what will happen if circles or ovals are considered? Of course, we cannot handle all shapes, but we can make use of a type of function with a very useful property to investigate on equidecomposability on common shapes with curves. Analytic functions are functions that can be characterized by a small interval of it. Then we define the direction distribution operator using the analytic function that describes the boundary of the shape using analytic functions. The rest is similar to the no rotation case. There is some limitation to our results. Only shapes with boundaries consisting of straight line segments are considered. Also, only shapes with finite parameter and area are considered. To conclude, equidecomposition is a profound topic that involves deep mathematical knowledge. Yet it is figurative, as one can do experiments on this using papers and scissors. Hope what I do in this project can add a small piece to the unbound realm of mathematics, and I hope it is for positive ways. Thank you for your attention.